So understanding the second derivative test for relative extrema is easier if you can visualize what's going on. So remember that one of the hypotheses of the second derivative test for relative extrema is that the first derivative has to equal 0. So I'm going to draw the only three circumstances that I could have in a graph if the first derivative was 0. So we could have something like that. We could have something like that. And we could have something like that. There's no other way on a graph that you could have a slope of 0 that looks anything different than one of these three things. So when I'm looking at the places, oops, it's supposed to be a 0 slope, didn't draw my lines very well, those places where the slopes are 0. Now, here, at that point, the slope is 0, but the graph is also concave down. And if you remember, concave down is implied by f double prime is less than 0. So if you have a slope of 0 and it's concave down, you can clearly see that's going to be a relative max. And that's where that conclusion comes from. If you have a relative min and the slope is 0, you notice that the graph is concave up. And concave up is implied by the second derivative being greater than 0. That's a relative min, hence this statement. Now, if the inflection is changing at the slope of 0, which it is here, it's neither concave up nor concave down, well, one of the hypotheses is that f of x has to be twice differentiable. And the only way that the function can be neither concave up nor concave down and is twice differentiable, meaning the second derivative exists, is if f double prime of x equals 0. And hence this conclusion.